In this question now, we have a bar with mass m and resistance r. It's in contact with vertical frictionless rails with width w. The bar is attached to a spring that has spring constant k. The equilibrium length of that spring with the bar attached is shown here by this dashed line. We pull it down some distance x and we let it go. All right, part A. Which way does the bar move after we let it go? Well, we've pulled it down, the spring is pulling it up, so it's going to move up. So up because the spring pulls it towards equilibrium. Next, what are the directions of the induced magnetic field and current while the bar is moving? So let's think about what's happening here. This is going to be a Lenz's law application. So our bar moves up. We're increasing, by moving the bar upwards, we're increasing the magnetic flux where the magnetic field points into the page. Lenz's law says that nature will always oppose whatever change we make. So if we make a region with more field pointing into the page, the induced magnetic field is going to have to point out of the page. And that's represented with a set of dots. Okay, so as bar moves up, the induced field B points out of page. And we know that's true from Lenz's law. What about our induced current? Well, let's think about what direction that current is going to flow in. If I imagine my hand around this lower section of the wire, my fingers go where the magnetic field are, sticking up out of the page. My thumb shows what the current is doing in this part of the wire. It's traveling to the right. So in this part of the wire, the current travels to the right. That means it comes around the entire circuit this way. So there is the induced current flow. Induced current I flows counterclockwise. And we got that from our right-hand rule. All right, part C. Draw the free body diagram for the bar while it is in motion. So let's draw our bar. What forces act on it? Well, it has a mass, so it does have the earth pulling down on it. That's the force due to gravity. It has the spring pulling up on it. That's the spring force. So last we need to know the direction of the magnetic force. The current moves to the right. The magnetic field is into the page. So I cross B gives us a magnetic force that points down. So I cross B is F. Magnetic force points down. So we got that one from the right-hand rule. Okay, there's our free body diagram. Next, find an expression for the magnetic force on the bar. So there's going to be a fairish amount of work to this part. Let's get started on it. We know for part D, magnetic force is equal to the current in the bar times the length of the bar crossed with the magnetic field it's sitting in. Okay, so that's going to be our current I. The length of the bar, it has a length W. Remember, the direction of the length vector is the same as the direction of the current. That's to the left. I'll put on my coordinate system where positive x is to the right. So the length of my bar is going to be W in the negative I direction. That's going to be crossed with my magnetic field. It has a magnitude of B. It points into the page. That's the negative K direction. So this is going to be I minus W minus B gives us I times W times B, I cross K. I cross K is equal to minus J. That's something we already knew, that the magnetic force was in the minus J direction. Minus I W B J hat. Okay, so we found an expression for the magnetic force here. We're not finished. We need to put in something for this current. So let's see how we're going to find the current. To figure out the current, let's remember Ohm's law that tells us that I is equal to epsilon divided by R. It's the potential divided by the resistance. How do we find the potential? Well, to find the potential, we can use Faraday's law. We know the magnitude of the potential is negative the change in magnetic flux divided by time. What's our magnetic flux? Well, magnetic flux is B dot A. Oh my goodness, my pen is given out. It's okay, I think I have another black one handy. B dot A. There, not exactly the same, but not too bad. B dot A is the magnitude of B times the magnitude of the area times the cosine of the angle between the magnetic field and the area. My magnetic field points into the page. I know that my area is perpendicular. It's either in or out of the page. I'm going to pick into the page. So B times A times cosine 0 equals B times A. What is the area of this loop? Well, it's a rectangle, so it's going to be length times width. Let's say that the length is symbolized with a lowercase l. Here's our length from here to here. So L times W gives me the length of, gives me the area of that loop. B times L times W. Okay, so coming back to my induced potential, I've got minus d by dt of B times L times W. Take the constants out front. Minus B and W are constant, dl by dt. dl by dt, that's the instantaneous velocity of that bar as it moves. B, W, V. So dl dt is just velocity. We're going to take the magnitude, so we've got plus B, W, V. Okay, come back to our current. Our current is the potential, B, W, V divided by R. We're going to put this in for our current, and it's going to give us something for our magnetic force. Magnetic force equals minus current, B times W times V divided by R times W times B J hat. Let's just neaten this up a tiny bit. Magnetic force equals minus, I got two B's, that's a B squared, two W's, W squared, V divided by the resistance J hat. Okay, so there's our expression for the magnetic force on the bar. Part E, write Newton's second law for the bar while it's in motion. So for our Newton's second law, that says we're going to say that the sum of the forces on the bar is mass times acceleration. Now, I should have written an uppercase M because that's given as an uppercase M. So for my forces, I've got my spring force up, that's positive. My magnetic and my gravitational forces point down, so I've got minus Fg minus Fb equals M times A. My spring force is given by Hooke's law, K times X. Weight is given by M times G. Magnetic force, I just sorted out, equals mass times acceleration. Okay, this is kind of an interesting result. Maybe we could stop here, but let's take it a little bit further. V is how fast this little expression x is changing. So v is the change in position over the change in time. So dx dt or dl dt, it's really the same thing. So for v right here, that's equal to dx by dt. Acceleration is the derivative of velocity, or the second derivative of position. Let's put all these things together. So k times x minus m times g minus b squared w squared over r dx by dt equals m second derivative of x with respect to time. Okay, I think now I'm going to divide all terms by m. And I'm going to get everything on the one side of the equation. So my second derivative of position with respect to time. And now I add on this term plus b squared w squared over m times r dx by dt. I'm going to do my x term next. I've got minus, yes, because I have to bring that to this side, that's going to make it minus k times x over m. And then as I bring this one over, that one becomes plus equals 0. This is a very interesting expression for Newton's second law, and this is going to help us answer part F. Part F says, describe the resulting motion of the bar and support your answer. Well, if we look at this equation, if we covered up this term, we would have acceleration with x. The acceleration would be proportional to the displacement. That would give us simple harmonic motion. That would simply bounce up and down. We, however, have this second term that depends on velocity. That means this is going to be damped oscillatory motion. And that makes sense. Our bar is going to oscillate up and down, but we're going to lose some energy through the resistance in the wire. That means it's going to lose some energy over time, and eventually those oscillations will die down and it will stop moving.